The intervals used for incremental search need not be uniform, as it is based on pure guessing. Check out these examples here in numerical solutions to CE problems. Roots are x-intercepts, so they differ from solutions. From the name itself, one only needs to determine the approximate root by using intervals. These intervals are identified by purely guessing. The second example works on a slightly longer polynomial of the function of x, which is equal to 3x raised to 4 minus 2x cubed minus 4x squared plus 2. We are still to look for a root nearest the origin, on the positive side, which means the root we are looking for should be positive. And just the same, we end when we have an accurate answer until 4 decimal zeros, using whole numbers as initial values. First is to determine the initial values. With the origin requirement, we start with x equal to 0. So the function becomes 3 of 0 raised to 4 minus twice of 0 cubed minus 4 times 0 squared plus 2. This gives 2. Let's also take x as 1, the function of which turns into 3 times 1 raised to 4 minus 2 times 1 cubed minus 4 times 1 squared plus 2, which becomes negative 1. The sign jump is already observed. If we illustrate the points, at x equal to 0, y is positive 2. When x is 1, y is equal to negative 1. We can join these 2 points to verify that there is a root between the span of x as 0 to positive 1. In this illustration, it is also observed that the root is nearer x of 1. First is to assume an interval of 0.1, and we are to start with the limit nearer 0, that is, as positive 1. Take note that the span considered is 0 to positive 1, and since we are using the upper limit, we need to subtract the increment. We take x as 0.9, so the function becomes 3 times 0.9 raised to 4 minus 2 times 0.9 cubed minus 4 times 0.9 squared plus 2, which results to negative 0.7297. This result is still far from 0, so we keep on iterating. We go another increment lower at x equal to 0.8. So the function is now 3 of 0.8 raised to 4 minus twice of 0.8 cubed minus 4 of 0.8 squared, then add 2, to get negative 0.3552. This shows progress as we are reaching 0. Take another increment, so plug in 0.7. The function then becomes thrice of 0.7 raised to 4 less 2 times 0.7 cubed minus 4 of 0.7 squared plus 2, to get positive 0.0743. This shows the jump, so we need to end our iteration. But since we have not reached the required accuracy yet, we solve for smaller intervals. But the limit used this time is with x equal to 0.7, as its result is nearer 0. Next is to use smaller intervals. Say we work on 0.01 for the span of 0.7 to 0.8, where we use 0.7 as the starting limit. With x equal to 0.71, the function is 3 times 0.71 raised to 4, minus twice of 0.71 cubed minus 4 times 0.71 squared plus 2, giving 0.030128. Continue with the next increment of x, which is 0.72. The function then becomes thrice of 0.72 raised to 4 less twice of 0.72 cubed minus 4 of 0.72 squared plus 2, which results to negative 0.013880. There is then the jump from positive to negative. The span is from 0.71 to 0.72. And we are to use the next limit with x as 0.72, as the accuracy isn't achieved yet. Let's then use increments of 0.001 and we use x of 0.72. With the span, we need to subtract the interval, starting with x of 0.719. The function then becomes 3 times of 0.719 raised to 4, minus 2 times 0.719 cubed, minus 4 times 0.719 squared, plus 2, giving negative 0.009488. Take the next with x of 0.718, where the function becomes thrice of 0.718 raised to 4, minus twice of 0.718 cubed, minus 4 times of 0.718 squared, plus 2, giving negative 0.005094. Take the next increment of 0.717. The function then is 3 of 0.717 raised to 4, minus 2 of 0.717 cubed, minus 4 of 0.717 squared plus 2, which results to negative 0.000070. Almost near zero, but still not reaching the accuracy required. So work on the next increment of 0.716. The function then is 3 times 0.716 raised to 4, minus 2 times 0.716 cubed, minus 4 of 0.716 squared plus 2, which is then positive 0.003701. With the jump finally appearing, we can stop the iteration, and we use x of 0.717 for the limit of the next increment. Knowing the span as between 0.716 to 0.717, we take an increment of 0.0001 and we use x of 0.717. As this is the upper limit, we subtract the increments. Start with x as 0.7169. So the function is thrice of 0.7169 raised to 4, less twice of 0.7169 cubed, minus 4 of 0.7169 squared plus 2, giving negative 0.000257. The next is 0.7168 plugged into the function, making 3 of 0.7168 raised to 4, minus twice of 0.7168 cubed, minus 4 of 0.7168 squared plus 2, resulting to 0.000182. Now we see the sign jump, but we still lack another decimal for the accuracy. Between the two values, we use x of 0.7168 for the next limit as it is nearer 0. This time, we use an interval of 0.00002 and start with x of 0.7168. This is the lower limit, so we add the increments, starting with x of 0.71682. Plugging this into the function, we would have f of x as 0.000094. Add another increment and have the function 3 times 0.71684 raised to 4 minus twice of 0.71684 cubed minus 4 of 0.71684 squared plus 2, resulting to 0.00006. Since this satisfies our accuracy, let's validate if the next increment will yield a larger gap. This time, instead of an interval of 0.00002, we use 0.00001, where x is then 0.71685. Plug this into the equation to come up with negative 0.000038. This is negative, which shows closeness to 0, but the gap from the origin is larger than the previous f of x, which means we use x of 0.71684. If the f of x is rounded to 4 decimal accuracy, it is rounded up to 0.00001, which still has 4 zeros, and this value is less than the last value of the increment we just iterated. This concludes the iteration with the root as 0.71684.